They didn't really overlap too much, at least last time.
Yeah. So
what were the two like big picture trends of discussion that we talked about?
So the two big picture trends was, the first one was data allocation. And when I say data allocation, I mean how to think about how stuff gets shelved into matrices.
Yep.
And then the other thing.
So how does stuff get shelved into matrices?
So say if we had.
So give me an image and give me text. Yeah, some text data.
Do you want text data or do you want like longitude, latitude data or something like along those lines?
Show me all three. Show me what we talked about for all three.
Because I don't think we ever really went truly into.
We never went deep into the text data, but that's fine. You can still explain to me what we did talk about.
We'll just do the same thing that we did last time, which was text machine.
Yeah.
And then Rod can pitch in on that.
I think it was talking machines.
Talking machines?
Okay.
Yeah.
What did I do? What did I bitch about?
You and Alex actually talked about this paper.
Oh yeah. The attention paper?
Yeah, the attention paper.
Mm-hmm.
Yeah.
So we did talking machines, then we'll just do
What is the talking machines?
so this.
So what we're doing right now is last time we talked about just in general, how do you organize data in machine learning and ML?
No.
With the idea being, why do we care about something like linear algebra? Why do we care about calculus? Why do we care about optimization? Like, what's the motivation behind learning all this shit in the first place, right?
Okay.
So that's where we started. Is like,
I didn't even.
Why
know.
do we care?
I don't even know
Yeah.
why we care.
Yeah. So I think starting with the
How did you figure out why we
motivation.
care?
What?
How did you figure out why we care?
I've done a lot of it. I've implemented stuff.
And then, so I'm just gonna do launch lat, but this time I'm gonna do something a little different where we did price last time. Or we actually did launch lat up here in price.
Good.
So let's draw it out.
And then we did price. I'm gonna do something different because
Sure.
I'm a cool
Yeah.
kid.
Let's change it up. So let's not even do longitude and latitude. Think of something else.
Okay, cool.
I think viewing the same thing from different perspectives is always what you want to do, in my opinion. I think every time you revisit an idea, you should approach it from a slightly different view angle, if possible. Nice. Perfect.
So we'll do vertices.
That's awesome.
And then what we're gonna do on top of those vertices is we're going to do the meshes that are associated with those vertices.
Sick.
So we're
I
gonna
love
do it by 3D, baby.
Nice.
So we're gonna call this, we'll do mesh.
Mm-hmm.
So we'll do the mesh that it's associated with, and then the face that it's associated with as well.
Nice.
So
what's, just so I know what a vertex
So-
is in terms of animation, but what is a
Yep.
mesh and a face?
So a mesh is, say we have a teapot, right? So
Mm-hmm.
I'm just gonna draw out a weird looking teapot that is ugly as shit.
Okay.
That's my teapot.
Yeah.
Yay! Looks like a little knight.
Yeah, and if you draw some pubic hairs here, it looks like a dick and balls.
Don't judge my teapot.
I kind of see
Alright.
what's it called? An elephant.
An elephant. I
Yeah.
see the elephant too.
Yeah. So now you don't. So we'll define this as the mesh,
Mhm.
and the mesh is made up of faces. So
Okay.
we'll say that these are the faces, and they're all quads.
Mm-hmm.
Besides the one down there, it's a tri, but in reality, since it goes around it, it's a
Mhm.
quad.
Yeah.
And so all of this mesh is made up of a matrix of quads.
Okay.
So imagine it like that, right?
So a mesh is defined by being a bunch of quads.
Yes.
And the
exactly.
quads are each what? Like
The
four-sided,
Quads are each four-sided.
and they're 2D,
so-
they're just planes.
Yep, and this is called a face.
Okay.
So the
Okay,
quad
cool.
itself is the face.
I see.
So this is the mesh. This is the overarching mesh.
Yeah.
This is a face.
Uh-huh.
So that's any face on that.
Yeah.
And then our vert1, vert2 is going to be verts within the actual mesh. Because when you make a face,
So the
The way-
vertices in a mesh are ordered, or
Yeah.
they're numbered at least.
they're numbered. And so the way to think about it is the only way to generate a face
Mm-hmm.
is to do it based off of verts.
Mm-hmm.
So the face is literally just verts being connected to each other. And
Okay.
that's it.
So the
Okay.
mesh is the compilation of all the faces and vertices.
I see.
In one place, right?
So give me an example of what would be these values here.
So what you would dictate is, so you said you have a mesh
Mm-hmm.
and it has verts that go all the way to n.
Yeah.
So we'll do vert 1, vert 2, vert 3, and then all the way down to vert n, right?
Mhm.
And then we want to know that are these verts associated with a specific mesh that we've indicated within our octree or whatever the hell we're making.
Yeah. So what would the value here be?
So depending on mesh, with vert, it would literally probably be, oh, man, that's maybe not the best thing because that would probably want to be a bool. So,
Yeah.
damn. Fuck. I thought that was so good. Damn. Okay.
Yeah.
What we'll do instead,
I was a bit sus.
instead of actually doing,
I like the vertices being the rows here. So what are some properties that you can measure about a vertex?
so you know what? We're gonna do, instead of mesh, we'll do transform.
Okay.
Actually, this will get your goose. This will make you
My
giddy.
goose.
X, Y.
Perfect.
We're just gonna dictate where it is on the
Yeah,
X,
yeah,
Y.
yeah, yeah. Perfect.
space.
That's awesome.
Do
Do we want to do? Oh, and I guess it's only X, Y, right? Because they exist on they exist on the mesh, right? So
They exist on the
so
mesh.
So you only need 2 coordinates to.
No, you'll need to see as well.
You need a Z.
Yeah, because the mesh is not flat. The mesh is in 3D space. So this is a 3-dimensional space that comes out multiple ways and it goes up.
Can
So
a
you-
vertex be inside of it? Does a vertex have to lie on the surface of that space?
It has to lie on the surface of the space.
So you actually could express it with only 2 numbers then, if
If
it
you
lies on
flatten
the
it.
surface of the space. Yeah.
Yeah, if you flatten it, you could.
Yeah,
Yes.
yeah. But I guess they use 3 numbers
Right.
just so that it's easier. you know,
Exactly.
so
Well,
everything is in the same.
In the end, right, it's still in a 3-dimensional space, so if you don't flatten the mesh, you still need to know where in Z it is.
Yeah,
Like,
yeah. So that's actually that will lead us into sort of an interesting and somewhat fundamental concept in linear algebra, which is the idea of the rank of a matrix. So I'm gonna intro this right now because I think I think we're gonna talk more about it later on. I don't think
Okay.
we're there yet, but there's this idea in linear algebra called rank, which is anytime you have a matrix, that matrix has a rank, and the rank of a matrix essentially tells you how many units of information it contains. So say you have 10 columns of information
okay.
in that matrix, and the rank of the matrix is 10. The way to think about that intuitively is that all 10 columns of that matrix are giving you information.
We'll just dictate the columns by these lines here.
Yeah, sure.
And we'll just,
Yeah. So if the rank of this matrix is 10, then all 10 columns are giving you information. That's how you can think about it. And
okay.
later when we talk about it more, I'll formalize what actually that means to say
Yeah.
giving you information, but just to give you an intuition right now. And if the rank of a matrix was 5, that essentially tells you that 5 of the columns are superfluous, right? You could delete
Right.
5 columns of the matrix.
They are non-existent. It doesn't matter.
And it would give you the same information, right?
Like
You might have to reorganize the information
Right.
and maybe look at it a different way, but you only essentially have 5 columns worth of information if you have a rank 5 matrix, even if it has 10 columns. So here, this is a great way to give you the intuition of rank, because here you have these points that live on a surface, and that surface is in 3 dimensions.
Right.
And you have these three dimensions that define where these points are, but because they live on a surface of this, you could unwrap this surface and then give them two-dimensional coordinates.
You can.
So what that means is that this is a rank 2, this is at most a rank 2 matrix because
So the way that's done is on V space.
yeah. So this matrix is at most rank 2 because you could reorganize the information. It turns out like this.
Yep.
And delete one of the columns, and you would have the same information as you had originally. There's no
see.
loss of information. So
Interesting, yeah.
so this concept of rank is gonna like pops up in machine learning a lot.
Yeah.
It turns out because knowing the rank of a matrix is sort of a quick and dirty way of like getting a decent look at like how much information you actually have contained, right? Like, do you have like all of the matrix that n times m rows times columns, like n times m values could possibly give you, or do you have some lower unit of information than that?
Right.
And so there's a lot of
So it's a quick way to compare.
yeah, and there's a lot of tools, especially in fundamental machine learning, where thinking about the rank of a matrix is useful.
I see.
And I'll go into those tools later, but some tools that involve projecting data from higher dimensions into low dimensions, you need to think about the rank of a matrix to like understand how those tools work. But
Okay.
I'm not going to go into that like
Yeah.
super deep right now, but this is sort of like introduction, like matrices have this thing called rank, and the rank tells you how much information the matrix
Right.
gives you. So, okay, so we've done this. I think this is great. This is a really great thing here. So now we have the image. So
Yep.
how did that work? Remind me.
So we dictated it based off of rows and cols. So we called it, I think we just dictated it like this.
Yeah, this
It
is
was
just a 2 by 2. Yeah, 2 pixels by 2 pixels.
And then what we were able to do is we were dictating it based off of color value. And so I'm assuming
So
that
what
would-
values did we assign each of these?
0, 1.
Let's just
So
put-
here's
yeah.
a question for you though,
Yeah.
because I didn't ask this last time.
Mm-hmm.
When you have an image like this and you have a matrix,
Yeah.
and obviously you want to probably keep it pretty simple to do 0
Yeah.
to 1.
Yeah.
Does the image, when you compress that image, does it convert that entire image? So say it's an RGB color, like red, blue, green channel,
Yeah.
and all of it.
Yeah.
Does it convert that to a grayscale and then give you out 0 to 1 values?
No, you store 3 different matrices, one for
I
the
see,
red,
one
one for the green, and
green,
one for the blue. Yeah.
Okay,
And
so
then you generally do operations on those matrices
yeah.
separately.
Okay, so for this,
By the
we'll
way,
just keep it simple.
here's a really interesting thing that ties into this.
Yeah,
Like JPEG compression
yeah,
uses rank fundamentally. So the
Really?
way that a JPEG compression works, fundamentally, is that it sort of says like, okay, we can kind of pretend that a matrix is lower rank than it is. Like we can shuffle it around, and we can, and in the shuffled version of it, we can take all of the columns that have the least information and just delete those columns. So we can say like, if it's close to a lower rank matrix,
yeah.
we can say that it actually is a lower rank matrix, delete all of the columns that contain almost no information, and then just keep that lower rank version of it that
That's weirdly
keeps
changing,
information.
like, and
Yeah.
that's been around for years.
JPEG, yeah, dude. I mean, linear algebra has been around for
I know, but it's,
Many
it's,
years.
it's, like, it's
Rank's been around
fascinating
since the
to know,
1800s.
like, it's fascinating to know that it was like that early on,
yeah,
and like just physical image generation.
yeah, totally.
So
So just to
yeah,
square this
so-
off, so how does this actually turn into
So-
a data table like we have
So
here?
what this would do is you would, like we talked about before,
Mhm.
the image would get separated like this, and then what would happen is it would literally just be defined by a matrix, or a matrix that just continues into space. So for this one, for example, it would be 1, 0, 1, 0, and then I'll get rid of that. So it'd be like that. Or no, what am I doing?
There we go. Yeah.
Sorry.
I was wondering when I should say.
Yeah, sorry.
Yeah.
I was not looking
Nice.
at it. Yeah.
Nice,
So it'd be
nice,
that.
good.
So it'd be 1, 0, 0, 1.
Yep. And then if you had another matrix, so say I have this matrix. Say I have a set of 2 matrices. The first one is this, and then the second one is this.
Mm-hmm.
So now what does our data matrix look like?
So our data matrix would be, we would be able to just do it by rows. So we dictate 1, then we dictate 2,
Mm-hmm.
and then it would literally just be by rows. And so we actually talked about this in depth last time.
Yeah.
Well, not really in depth, but at least a decent amount of information going into this about how dimensions. So this is on a 4-dimension plane, right? This is 4 dimensions.
Yep. Yeah. Good.
And
So,
so-
let's start getting into geometry here.
And so we talked about that. Depending on the dimensionality, the only way for matrices.
So by the way, just for you. So what we're doing right now, do you see what we're doing here? Yeah. So we're taking the 2x2 image, we're unwrapping it. That's called vectorizing.
Yeah.
We're turning it into a row vector, and then we're stacking different images on top of each other as row vectors. So that's
Oh,
usually
you're stacking that on top of each
yeah.
Okay,
So
okay.
this row represents the first image,
Yeah.
and this row represents the second image, right?
Yeah.
And we see we have 1, 0,
0,
0, 1,
Yeah.
and then we have 0, 0, 1, 1, like that. And then if we can add as many images as we
Right.
want. If we had and if we had images in a normal size of an image, say 256 by 256, what we do is we would unwrap that into a 256 times 256 length row vector, a super long one, and then we would just stack it.
Yeah.
And we would still have 3. By the way, okay, so here's a good exercise. So now say these are RGB. So
Yeah.
now how does that change things? What do we do if they're RGB?
Oh, interesting. Okay. So if they're RGB, we then need. It's not. Where's the fucking eraser? I'll just grab this guy. So if it's RGB, then we actually need it to dictate not to 0 to 1, but then it would actually need to. Okay. It would be a matrix of the red, green, blue channel. So you'd probably want it to be 1, 0. So let me just convert this. I'm going to assume. So we'll just call this red, green, blue.
Mm-hmm.
And then each of these value sets would have values within them
Mhm.
to dictate what it would be. And I'm unsure if I would want it to just dictate a general thing, or what you could do is you could do it based off of.
So what are the values on the columns?
So the columns are. Trying to think actually back to like what it would be in Photoshop.
Mm-hmm.
It would be hue, saturation, and then alpha potentially at the bottom. So like if you wanted to make it even PNG, you'd have alpha at the bottom.
Yeah.
I think it would be 3 numbers.
So now what if you add another image? How
If
do
you
you-
added another image,
Yeah, so
it
you
would
have
be
2 images instead of
it
one.
would be this on top of another one. So
Okay, so you think it would go RGB, 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 RGB like that? That's how you think it would be organized?
No, I don't think it would be RGB, RGB, RGB. I think what it would be is it would be the first image, which would be R. You'd put all the R information. So say we'll just put some arbitrary numbers in here
Mhm.
just to do some shit.
Yeah.
1, then 0, 0, 1.
Mm-hmm.
So the way it would roll out is it would still be a single row, but then it would be 0, 1, 0, 1, 0, 1, 0, 0, 1. And that would be your image.
Wait, so where did you get the 0, 1, 0, 1, 0, 1, 0, 0, 1 from?
I'm just dictating an arbitrary value
Okay,
in
so,
there,
Okay,
just so I could explain how it would be packaged into a matrix.
got it.
Yeah. So yeah. So I think this brings an important consideration into account that there's a lot of different ways to represent information.
Yeah.
People actually do this in practice a lot of the time, right?
Is
so
this- is
they'll
it-
concatenate the red, green, and blue channels.
Is this like it's obviously viable, but is it? I feel like it's not that you're going to lose information. It gets muddy to read at a point.
Yeah, but that's fine, right? I mean, how you organize it, if you organize something differently, then it's just a different organizational structure a lot of the time, right? Like you can organize it however you want as long as you don't lose information, and most of the time it'll be the same result. So
I need to have my computer look up Photoshop.
yeah,
See
yeah.
what-
So I'm not sure if they organize stuff like that in practice. I do know that they sometimes organize stuff like this, and often what you'll see is just you'll see.
I see. So it will be like
So
this.
it'll just be kept, and these are distinct, right?
Yeah.
It'll just be kept as 3 separate objects a lot of the time, right?
Uh-huh.
And then you just stack these rows like this.
I see.
Oftentimes you'll just have 3 matrices, right? You'll have
Right.
one green matrix, one red matrix, and one blue matrix.
Yep.
And then the nice thing is that in practice, you know, with something like PyTorch, which or NumPy, which is what ML practitioners would actually use in practice to store data, you have this 3-dimensional array. So
Right.
so you could store data like you could store data into one array, but it would be the first dimension is the stacks of think of a cube,
Okay.
right? And stacked on top of each other are images.
Okay.
And then, sorry, it's a cube.
Do you want to draw it real quick?
Yeah. So you can think about it like this. So you can think about it like, right, you have, it doesn't actually matter how you organize it. So I would say it would be like, say you have 2, so this would be your R layer, this would be your B layer, and this would be your G layer, like this, right?
Yeah, I
Layers
see.
like this,
Yeah,
right?
yeah.
And then in the R layer, you would have, your first 0, 1, 0. This would be your first image, and then you would have a second image here, and so on, right? So you would vectorize it the way that we talked about, but then you would just stack the red, the blue, and the green layers.
Yeah, you know what's really interesting about this? This kind of gets back to how animation was first made.
Yeah.
Like for Walt Disney,
Mhm.
when they wanted to add layers to it, they
Yeah.
would have glass that
Uh-huh.
would be seen through pretty much. And so they
Oh.
would just stack the glass.
Oh, that's cool. Yeah. So it's kind of like that.
Yeah.
Yeah. It's very similar.
I've seen a video of that on YouTube.
Yeah. But I just want us to get used to. So that is the same data structure as that 2D thing. So this is literally, imagine this, but then there's like layers of that,
Yeah.
right? So like you take this plane and then you just add 2 more planes
Right.
behind it.
And I kind of wanted to talk about that real quick.
Mhm.
So we talked about this last time.
Yeah.
Where it's like, so here's something for you, Rod. So say we have 256 by 256, right? So by 256. And then we have, say, 50 images of these. What that means is it would be 50 dimensions of that. Well, would it be 50 dimensions, or would it be this number of dimensions with 50 images?
It would be.
It would be this many dimensions. That's right. So it would be however many this comes out to.
Yeah.
And then that would be our dimensions that are in our matrix.
No. It'd be
And
2 to
then-
the 16th.
Yeah. I think so.
So how did I get 2 to the 16th so fast? We're gonna do another divergence here.
Yeah.
What is 2? Oh, how do you get 256? What is 2 to the power of what gives you 256?
256 is, what is it? The worst part is I use this so often that I don't even think about the powers anymore. They just like naturally come to the brain
Yeah.
because every texture ever is defined by powers of 2. So hold on.
I'll give you a hint, I'm taking advantage of something that we talked about last time, a mathematical property that we talked a lot about last time.
Logarithms?
I'm taking advantage of the mathematical properties of logarithms to do that calculation.
Are you?
Mhm. Try drawing it out. Try turning 256 into 2 to the something.
I feel like I was doing the same thing, except I just never stopped to think that I was taking advantage of logarithms.
So log 56.
Oh, you don't.
Well,
you
yeah,
don't
I-
need to raise it to the power of 2. Just do the 256.
Yeah.
Just log 256?
Mm-hmm.
Okay.
Log base 2 of 256.
Oh, log
So
base
it's
2.
base 2. Yeah.
So I'm obviously, what I could do is I could just run through my brain and understand what I want, but I'm interested in potentially how you guys did the log, because since it's log base 2,
Mm-hmm.
it's different than what we did last time where we did log base or log base e
Mm-hmm.
and log base 10.
Yeah.
Yeah.
So
obviously-
actually, so thinking about let's add log base 2 as something that we use as a standard base to think through logarithms.
And literally all it would be is, I'm gonna move this 50 over here because I want to have it be a clear space.
So before we get into this, what did we talk about before in terms of like before we even think about the calculations, intuitively, like what does a logarithm feel like? Like what if you take the log of x?
Yeah.
How is that warping the space of x?
Well, it depends on what graph we're warping it, right? If we're taking it with logarithmic.
No, don't think about
Don't do
graphs.
graphs.
Just think about the function itself. In general, like intuitively, how should you think about what the function is doing to any number that you give it?
Depending if we're going backwards or forwards, we're either dividing or multiplying by the base.
Sure.
And so, depending on if we're going forwards,
I wouldn't say we're dividing or multiplying by the base. I would say that the logarithm captures a property of what happens when we divide or multiply by the base.
okay, so the function outputs.
Yeah.
Is that a better way of saying it?
Yeah, I would say it hints at a relationship between addition and multiplication.
Yep.
Is how I would
Yeah,
phrase it.
that's fair.
But even simpler than that, just like, how does it feel to take a logarithm? How does it feel to take a logarithm of a huge number?
Oh, it feels great because you're compressing it.
Yeah, great. And
It feels real good.
so that's the feeling you should get when you think of what a logarithm does. Is like it turns huge numbers into like pretty small numbers. Yeah, it turns massive numbers into like very reasonable numbers, right?
Right.
10 to the 500
Yeah.
is a fucking ridiculous number, right?
Yes.
That's like many orders of magnitude more than there are atoms in the. That's if you took all of the atoms in the universe, and then you made each of those. You made the entire universe one atom, and then you made an entire and then you made an entire other universe where each of the atoms of the new universe contains as many atoms as the original universe. You wouldn't even get close to 10 to the 500. And the log base 10 of 10 to the 500 is 500. So, so logarithms are you should fundamentally think of logarithms as a function that takes massively ridiculous numbers
And
and turns them into
compresses
like something that you could count
Right.
to easily.
So my question is, for this scenario, right? Because the way we did last time is we started with 2 and then we went all the way down. And artistically, if I was to do that here,
Yeah.
then I'd be like, oh, obviously, but that would take a lot of time. So my question to you, and Rod, since you also didn't realize you were using logs, but then you kind of looked at it, what was the trick that you used to validate getting in, like, I understand the fundamentals of being able to take a log of a very large number,
Yeah.
and using that to compress it down by the base.
Mm-hmm.
But that still brings into the question of figuring out how many times the base goes into that number.
So how many times does the base go into that number? How would you figure that out?
I would have to do it. I would do base multiplication. I would just do 2 times 2 times 2 times 2 times 2
Yeah.
times 2
Yeah,
times
yeah.
2, right, over and over and
Yeah.
over again.
Yeah, exactly. And so the logarithm is telling you how many times you had to multiply 2.
Right, exactly.
So so how many times do you have to multiply 2 by to get to 256?
I was like, what is this sound?